Hello, everybody. Welcome to the EEMS introduction lecture for the EE modeling system training. In this lecture, we'll talk about what is EFDC Explorer modeling system, what are the different parts of this framework, and the overview will go through the different parts of this framework. We'll show a little bit about the EFDC plus graphical user interface, talk about some of the model setup, model calibration, show a couple of examples, and that will set you up for the entire training. So this graphic actually explains the whole EEMS framework, and it will show you how we progress through the entire framework. So first we start with a natural environment here. So natural environment here could be a coastal system, a river, a lake, or these kind of things that we want to model and represent mathematically. To develop a model for this natural environment, we have to divide this physical structure or physical feature into small grids. That gridding is done using the software CVL Grid. It's a two-dimensional grid generator. And what this process does is it divides the river or the lake or the coastal system into smaller grids, and those grids can then be simulated in the EFDC plus. So the CVL grid can be used to build curvilinear grids that are used for more complicated physical systems, and I will show a couple of examples of that later on. Once the grids are developed, then those grids can be imported into EE, which stands for EFDC Explorer. EE is actually a system where you can bring the grid, you can provide the different boundary conditions that could be flow or meteorological conditions, parameters for different modules that you want to simulate. Once you go through that process, a model is ready. Sometimes you may have to go back to redesign the grid or redivide the grids. Sometimes you have to make the grid coarser, and sometimes you have to make the grid finer. You can go back to CVL grid and do that process and then bring that grid, open it back in EE. Once the model is ready in EFDC Explorer, then EFDC Explorer helps you make the model and helps you run the EFDC Plus software. So EFDC Plus is the main engine that does all the computation. It's built on Fortran, and we'll talk about that a little later. But once the EFDC Plus runs, it produces outputs. Those outputs can again be visualized in EE, and you can look at it and change the parameters. Again, go back and redo the grids if needed. And you can generate animations or post-processing graphs, post-processed graphs, or you can generate statistics that can help you get some idea about how your model is performing, and if those results are useful, and if you need to do calibration again. Once this process is done, you can generate these reports with EE, and based on the results that you have obtained, you can make the scientifically sound recommendation in the final project report. And those recommendations can be applied to the natural environment. And sometimes you may have to go back and redo the model, come up with a next phase of model with more details or things like that. But in general, this is the whole cycle through which the EEMS framework helps you through this whole process. And we'll look at these parts of this framework separately as we go along. So this whole picture actually sets up the whole EEMS framework design in one visual. So first is the CVL grid. It's a curvilinear orthogonal grid generator. And as you can see, this is a complex water body that is shown here in the example picture. And grids are used to divide that water body in different parts so that the mathematical calculation for every small grid can be done. So it's a CVL grid is a general grid generator and can generate curvilinear orthogonal grid. Orthogonal grid means the cells are 90 degree or close to 90 degree with each other. If the grids are not 90 degree or they are if the grids have a very high angle among them, then it can cause mathematical instability issues. So CVL grid tries to or helps you to make sure that you can generate the grids that are very close to orthogonal. And they're a key component when with these kind of grid numerical models. And although it has been optimized for EEMS and EFDC plus, you can import the grid generic files from other software or export it into for other software. So CVL Grid can help you create brand new grids for the domain that has not been divided before. You can bring in existing grid, edit them, modify them, make a basic EFDC model, and you can export these grids in different formats, sometimes for different models, sometimes just for communication. We oftentimes export these grid and shape files or KML files to send it to our client so that they can look at those grids and say, okay, if those areas are represented the way they wanted to see it. So KML grids helps us. KML files can be opened easily in Google Earth. So any user who does not have access to EEMS or any other GIS software, Google Earth is free, so they can just open the KML file and look at the grid in detail. And then you can, in CVL Grid, you can also bring in an existing EFDC model and change or improve upon the grid. So these are some of the key features that orthogonalization, that means it helps you make the grid as a close 90 degree as possible. You can break grids, you can make grids for different places and then combine them, or you can take an existing grid and coarsen it, or so that you can merge multiple grids into lower number of grids, or make them fine. You can make a telescoping grid. In the telescoping grid, the size of the grid slowly changes, and a lot of the cases when you have the natural environment that is not straight, so river, there is sinuosity rivers, or the boundaries of the lakes and rivers is not straight, you can fit these grid edges for these polylines, and then it helps you generate the other support files that includes the background images, DEMs, etc. These are the resources for CVL Grid that are available on the EEMS website. It's eemodelingsystem.com. And there are multiple resources, and some of these resources are listed here, that shows the existing grid for some of these models that have been developed in the past. And you can just download these grids and understand how it works, and probably get an idea of how you're going to develop your own grid. And those links are available here, or you can go to EE Modeling System and search through these resources. Then we move on to EFDC+. EFDC stands for Environmental Fluid Dynamics Code, and the enhancements that are the specialty of DSI makes it EFDC+. So it's EFDC is a general purpose modeling software. It can simulate one-dimensional, two-dimensional, and three-dimensional flow, transport, and several biogeochemical processes that are happening in these kind of system. That would include the sediment flow, the sediment transport, eutrophication, these kind of things. The original AFDC software was developed by Virginia Institute of Marine Science in about 1996. Since then, EFDC has been a public modeling software. Functionally, it is equivalent to some other software like Mike21, Delft3D. EFDC Plus is the DSI's enhanced and optimized version, and there's some optimization that we'll describe as we move along. So this is a feature overview, and EFDC Plus mode has more features than a regular EFDC. It can do 1, 2, and 3-dimensional cable and sigma Z layering, where the different layers can have different number of cells. It can simulate wind circulation, temperature, heat, a full heat balance that can help you simulate the temperature of the water. The temperature of the water can affect the ice formation, ice melt. It simulates the vegetation that affects the transport of water, the energy loss due to vegetation, wetting and drying of the cells that are in the periphery. Conservative tracers, it can simulate unlimited number of tracers, and it is used for Lagrangian particle tracking and oil spill kind of cases. And you can also simulate how the hydrodynamic behaves going through a hydraulic structure. In eutrophication, it uses the model from CE-Qual. It's ICM kinetic, and it has multiple state variables, simulates sediment diagenesis and rooted plant epiphytes. Sediment transport, it has original approach and ZZLZ approach, and you can specify different number of classes, and the movement of those classes depends upon the energy of the water. And you can divide them into cohesive and non-cohesive. In some cases, you can have the hard bottom so that there's no erosion from the surface of the water body. It can simulate different metals, and it is coupled to ZZLJ or or to the original sediment approach, and degradation and volatilization of these toxics helps you simulate the concentration of them. It's EFDC, the original one is and EFDC Plus. It's widely used all over the world. There are different versions available in different places depending upon who the developer is. But primarily, it has a robust computational engine, and that is why it is applicable, and that is why it is accepted world over, and it is used by regulatory agencies like US EPA. And they use the EFDC for routine water quality management projects. In fact, the environmental regulators in China developed guidance for supporting the use of EFDC. And there are researchers the world over who are using EFDC for the research, and there's a healthy number of users for EFDC Plus, that is the DSI version, along with the entire EEMS. So this development history will not go through in a lot of detail. It goes through, it just tells you that when it was developed. Tetra Tech developed it in 1996. The first version EFDC underscore TT was in 1996. Then different versions came along. The 3 timeline solutions for hydrodynamics only. Then EFDC EPA version, that if you go to the EPA website, and that you can get the EFDC EPA version, and it's available there, but it does not have a source code, and there has not been any update on the EPA version since that time. At Sandia National Lab added some features to EFDC. Then DSI also had its own version that is called EFDC underscore DSI, and the one that comes with EEMS is EFDC Plus. It is based on EFDC underscore DSI, and DSI maintains this version actively, and we are constantly adding new features to it. This is an overview of a different way of presenting the same information. That at different times from 1990 onwards, it was developed by Virginia Institute of Marine Science, then Tetra Tech, then Sandia National Lab, and DSI LLC. Submodules have come along at different points of time. In dynamic memory allocation was in the DSI version in 2002. Later on, there was an open MP implementation, so you can run it faster. Currently, DSI is working on the MPI implementation. We are testing it at our offices. where it can the runtime speed can be greatly increased. These are some of the boundary conditions that were added at different points of time, and EFDC Plus added a lot of other boundary conditions, especially the hydraulic structures, some of the new open boundaries, and the flow boundaries. These are the different submodules that were added depending upon the developer. As you can see, EFDC Plus version had a lot of new submodules added, which is the version that you get with EEMS. So now we move on to the graphical user interface for EFDC Plus, that is the EFDC Explorer. So this is the software that is used to create a new EFDC Plus model, change the parameters, and make the model file so that you can run it with EFDC. So in the center, if you see, there's a EFDC Explorer, the interface. It creates the .inp file, and it reads the data from the different time series and information that you provide. It's you can also save the model settings here, and it works as a preprocessor and makes the files for the EFDC. Once the EFDC is run, EFDC Explorer can look at the output and suggest you can look at the results and make changes and prepare new sets of files for the new EFDC model. This is an interface for the EFDC Explorer. It looks like any other graphical user interface. Some of the obvious things that you can look here are this is for the making a new model, opening an existing model, saving the model, running the EFDC, the main engine. This you can look at the grid map, two-dimensional horizontal view of all the grid, three-dimensional view. You can look at the time series, use it to develop time series, and these are the different options up top that helps you drill down into the details of what other things are available. And this option can be used to look at the animation of the physical processes that you are simulating with the EFDC Plus. As you move along in the training, you will be able to use a lot of these options. You'll be able to generate output, and you'll be using these options again and again. This is a model control. This is a new form that we have come up with for AFDC Explorer that helps put the information of the entire model in one form, and it can be exported as HTML that you can look at and change or add or remove modules. So for example, from here, you can go to the grid on how the grid looks like, add layers to it, change grids, assign boundary conditions. You can add modules. This is hydrodynamics, temperature, and dye. You can add water quality into it, sediment into it. Timing and linkages helps you figure out what is the time period of the simulation, if you want to increase or decrease the simulation period or the simulation time step. You can change the initial conditions by going through this tab. You can add external forcing data, boundary conditions, and model analysis through this model control form. This whole form with its tabbed interface and the drop-down menu on the left side actually helps you navigate through different aspects of the model. So this is a two-dimensional view of one of the models that you'll be working on during the exercise. And this is just an example. So if you look at it, it shows on the left side, you will see that the line is a model grid. So these horizontal lines are the model grids, horizontal and vertical lines. So you see it's divided into perfect squares. And these values, blue value shows 7.16 meter bottom elevation, and red line is 10.8 meter bottom elevation. So you can see that the bottom elevation is higher in the periphery, lower in the middle. And so this is a pictorial representation of the entire elevation data for that for the lake. And on This side is a layer control. You can turn on and off layer. You can add, after you run the model, you could add new things to it. You could bring temperature and see how temperature changes over time or over the different locations or the concentration of nutrients, etc. This is a vertical view, and in this example that we are seeing that its temperature 24.921 is the blue, 26.165 is the red temperature. So temperature on the boundaries is higher, temperature inside the lake is lower, and you can set this as a animation also, and we'll see some examples as we go through. This is cut through column I equals 1. So for one column, this is the vertical view of the temperature. And on this side is the elevation. You can see the elevation goes from about 7 to 11.5. So we see the value of temperature for different elevation. This is a three-dimensional view, and so you can see the temperature for that whole lake as a whole. So you can see the temperature from low temperature to high temperature, and as you can see, the center areas are at lower temperature and the peripheries are at higher temperature. And these are a couple of examples that we'll talk about. Lake Washington is in near Seattle. So we are in Edmonds. This is the Lake Washington. This is a model domain. It's a very big lake, and so you can see there are about 1,100 cells, and some cells are 85 meters. Some cells are almost half a kilometer long, and as you can see, the color here, minus 60 is the bottom elevation of blue color, shown by blue color, and 6 is the bottom elevation shown by red color. So you can see that this area is the deepest part of the lake, and the lake elevation and the bottom elevation increases in this part and is high in the peripheries. And this the lake connects to the Puget Sound through this area. So this is an example of Lake Washington. And what we did was that in this case, we simulated a temperature. So we are showing some example results of this location in the Lake Washington, where we had the observed data observed by the Lake Washington buoy at different times. So we are showing some examples. So when we look at some of these examples, look at this date. This is the date. This is the time when the temperature was measured. The red dots are the actual measured temperature. The blue line is the simulated water temperature. So as you can see, this is June. The temperature at the surface, that is the lower, the elevation value is about 6-7 meters. The temperature is about 16-17 degrees Celsius, and at the bottom at about minus 54 meter, the temperature is about 656 degrees Celsius. And the blue line shows that we are simulating that well. In June, and further as we move along in that month, actually it's the same day. In the afternoon, the temperature on the surface increases further. And this is July of the same year. The temperature on the surface increases further, and we see this kind of distribution where temperature at the surface is higher, temperature at the bottom is lower. But as we move into March, which is spring is just starting, so the temperature is cold everywhere, and it's a similar temperature profile at the bottom and at the top, and our model is simulating the temperature extremely well. And these are both March values. One is in the afternoon, one is in the morning, but they both are low values, and our model is simulating it very well. As we move into April, the temperature at the surface starts going up a little bit, and in May, the temperature on the surface has gone above 10 degrees Celsius, and our model is replicating that process. So the next example that I'm showing is Newtown Creek in New York. And Newton Creek has a there we have several different sources that are actually feeding into the Newton Creek. And what we have done in here is that depending upon the sources, we have called them a die, and it's actually to visualize the effect of different sources. So as I will show in couple of in animation later on. So depending upon what source it is coming from, you will be able to look at the color and see if there is an effect of that source or not. So this is an animation, and there are 4 animations going on the same panel. First, I would like you to focus on the top left. This is a timing pane that shows the tide. So you can see that as the time change, the tides change. This is the combined sewer overflow. So from the combined sewer overflow, the water is coming. And this color shows the salinity. If it's blue, it's 0 salinity. If it's red, it's 23 ppt. And it's depth average. As you can see, the salinity here in these areas are a little lower, but due to the location of this Newton Creek, the salinity does not change a whole lot in the entire system. So some of these areas have lower salinity, but otherwise it's 23 ppt for the almost the time period that we are looking at. Now let's look at the top right. This is, or instead actually look at bottom left. So it says English Kills. English Kills is a source. So if the water is coming from English, if it is red color, that means the concentration is 10 milligram per liter, or that the water is coming from the English Kill. And so if entire thing is blue, that means there is no effect of water coming from English Kill. English Kill is not a significant source. If the entire of this becomes red, that means all the water is coming from English Kills. And so that shows us, helps us evaluate how much effect of English Kills source is. So as you can see that this effect of the English Kills is mostly you can see from here. At other places, it's still blue. So the effect, as soon as this water comes in here, it mixes with other different sources, and the effect of English Kills reduces a lot. And as soon as this the CSO event happens here, you will see the color of this will change, will become red or more redder to go towards red. And very soon, as soon as the CSO event stops, the color changes back again. So here, light blue here. Now again, it has become red here after the CSO event happened here. So this is head north. So that means the source from north. So if from the headwater north is coming, so if it is entirely red, that means there's an effect of the water coming from the north source. So depending upon the timing and depending upon the tide timing, you can see that there is effect of the head north event. And this is head south. So in a different direction, and so the water that is coming from the south side. So if it is red, that means there's as you can see, these are exactly inverted with each other because we wanted to see the effect of other different sources here. But you will see the more difference in these parts. So you can actually see this, like where the water is coming from the north boundary or the south boundary. The user support for EEMS is available through the website, knowledge base. There's demo version that is available for EEMS that is free. There's a user community forum where people post questions and you can get answers from the community as such. EE Modeling System website has links to all these sources. There's a whole host of video tutorials on YouTube that you can find the link through here. There's knowledge base, which is equivalent to the user guide for EEMS. This is a link for the trainings. You can find existing data sources, data sets, free grids, some of the models that have been used for test case to verify EFDC plus. You can download some demo models, and demo models you can open with the EEMS, with the demo version of EEMS, which is available for free. You can go to these forums and you can ask questions, and sometimes our colleagues at DSI will answer that. Sometimes other users answer that, but we try to answer these questions as soon as possible. Again, this is knowledge base is equivalent to the EEMS users manual, and you can go through this knowledge base and explore and search easily if you have a question about certain parts of the EEMS user interface. You can download a demo version for free. It has full capability of EEMS, and you can load and view any existing EFDC model. You can make your own model, provided it's pretty small, less than 300 cells. And a lot of examples that are available on the website that you can download it. This is the website for the demo version. And these are some of the links that are in the web and social media that you can join these or email us. And hopefully we'll be able to help each other learn more and do some good modeling. Thank you so much for your attention. If you have any questions, please feel free to ask them or post them through all of these sources available. Thank you.